Hi, everyone. Thank you all for coming. I hope you've enjoyed the conference so far as much as I have. And one of the things whenever I come to a conference like this is I'm just always amazed at the sheer amount of organization that is needed to put it together. If you think about even just the very basic things like the chairs in this room or the microphone into which I'm speaking now, these things are always very complicated, both logistically and also technologically. And whenever I get thinking about this, I always think about how at some point there was a first of these things. There was a first microphone, maybe prototypically there was a first chair, but humans have always been sitting down. And at some point, that was made by a person who sat in a room, maybe a mad scientist or someone with some resources, and they discovered something and they made it. And then what happened over time was we got very good at making those things to fit particular profiles. These chairs here, for example, they're not particularly ornate, they're not necessarily particularly interesting even, but they're easy to stack. They're probably relatively comfortable. And crucially, they match the color scheme and the price. This happens with all things that go from being artisanal, made in some regular way by some person very carefully, to what we would now term as industrialization. And one of the great things about industrialization is that it means that you can make things and then map them to these criteria that I mentioned earlier. The reason why I bring this up is, I'm sure you've all noticed, but AI is really beginning to undergo an industrialization. For a long time, models that were made were really kind of made based on gut feeling and some clever guy that you knew who had an idea about how to do this. And the applications were also not particularly useful. I think it was Faraday who said when electricity was discovered, what use is a new baby? Sometimes when you create these things, it's not clear how you will use them. You just hope that there will be some use for them. And I think for a long time, AI was in a similar place, right? All of these things were coming out, but ultimately all you could really do was interact with a chatbot. And now if you look where we are in 2025 going into 2026, it should be clear that there are lots of very useful and economically viable uses of AI that people want to deploy inside businesses, and they want to benefit from what AI can give them. I also think very crucially, if you look at the language that companies are using and the industry is using to talk about AI, we hear NVIDIA talking about AI for the factory age. You're going to hear me today talking about a model factory. All of these companies are really hinting at how much AI is scaling up. One thing we're really bad at doing as an industry is talking about how we build models. Occasionally, a model might come out, and you'll get some nice new model card and maybe some eval scores. Maybe if you're lucky, like with a DeepSeek, you'll get a paper. But that doesn't really begin to cover the real technicalities and difficulties behind actually building foundation models at scale. As an industry, we're really bad at this, and I think it comes from a place of fear about giving away some secret sauce. We don't really talk about, the tricks or the things that we have to do, or even the battles that we fought to build models that actually matter. And quite frankly, I think this is quite ridiculous, because the ideas are very cheap. It's execution that matters. And I want to be very clear, I'm here to talk today about Poolside and how we build models in our model factory. But I guarantee you that every company that is at the frontier has a version of this. I can only speak to ours, because I've only worked here and I only know about this. But I'm pretty sure that your OpenAIs, your Anthropics, your XAIs, all of these companies have a similar thing. This is what you need to be at the frontier. This is what we have used to get to the frontier. And I want to spend some time today talking to you about how this works and how it will enable us to continue improving our models going forward into the future. Now, I think it's worth starting from the beginning. So those of you who have trained models in the past will be familiar with a workflow that looks something like this. So to give you an analogy, let's imagine that we wanted to build a model that was really good at imitating Shakespeare. And we're going to do it in this old-fashioned way. What we would first do is we would first decide on some data set. That might be Shakespeare's sonnets. That might be English language. That might be code even in some senses. But it could equally be something that I've gotten some guy down the pub. Right? There's not really any way here to interrogate what our data set should be. We just choose one and hope that it turns out to be a good data set, again, based on our intuitions. Once we have that data set, we're going to feed it into what's called pre-training, which is this process of doing next token prediction, computing the loss. Believe me, I could go into that for a long time, but I won't. And again, there are lots of decisions that you need to make here that in this model, we simply cannot interrogate in any scientific way, right? I might have some intuitions about the architecture that I need to make a good model. My friends might have some intuitions about what makes a good model from an architectural perspective. But there's no real way of discovering how we could have done better. And equally, once we've finally done this pre-training, and believe me, there's a lot that goes into it, we get into the stage at the end called fine-tuning. And this is the bit where we take this person or this model that we've taught to write Shakespeare, and we give them detailed instructions of what it is they should do. So you can imagine, much like a child that goes through primary education, they get to the end of their life, and then you give them they get to the end of their school life, and then you give them some specific training. So maybe they want to be a doctor, maybe they want to be a computer scientist, whatever it is. You give them some particular training. And again, what's really crucial here is that this is just one model out of an infinite number that we could have trained, right? At any point along here, we could have made a different decision that would have led to a different and maybe better model. But with this, you have no way of knowing how your model could have been better or what you could have done to make it better. We have no insight into how good the data set was at actually making our model good at Shakespeare, right? Maybe the trick to getting a model that writes good sonnets is to expose it to French or German or Greek. We don't have any insight into that. Equally, for some number of parameters or for some fine-tuning strategy, we're just stuck assuming that the model that we have is good. Even if we trained multiple models, maybe we had multiple physical hypotheses, and we think, oh, you know what, I'm just going to sit there and repeat this process vertically many times. That is a really heavy engineering task. You would need a huge team to do this, because there's so many things that you need to get this right, that there's just in this form, there's a huge amount of manual intervention that is needed. Pre-training, for example, is a notoriously buggy process. Nodes die. You need to make sure that your training is stable and doesn't restart. And doing all of that manually is impossible. You would need a huge team to do this in some way that actually enabled you to be productive. And I really want to narrow in on this point, which is that there is a very large gap, both in terms of the headcount that you need and the talent of your employees and, quite frankly, the systems that you've built, to go between training one model to training many models at an industrial scale. And again, this kind of comes back to what I was saying about the chair earlier on. It's very easy for one person to make a chair. One skilled carpenter can probably knock out a chair very quickly. But making the number of chairs that are in this room, let alone at this conference, is a much bigger challenge. And crucially, doing it in the old-fashioned artisanal way is very slow. Right? You need to sit down, you need to have ideas, you need to run this very buggy training process. That's really tough. And it means that it's very easy to fall behind where everyone else is. Because there's always someone who's going to be smarter than you, more resourced than you, and you can't scale that way if you want to compete with these much larger companies in the way that we do. So I've said a lot about how you can take, or how you want to improve a model that you've trained. But one of the good things is to have some objective way to do this. So this is quite common in the industry now. Whenever a model card comes out, you'll see evaluation scores across various benchmarks. And actually, it turns out that it's really useful to be able to deploy these evaluations almost anywhere. So here you'll see that we have this on the pre-training block. But actually, this is something that makes sense to have also at the end or at the beginning, in fact, throughout training. One of the reasons why this is really useful is because as you go over your data set, your model could get worse, right? It could be the case that your model picks up some bad information, right? Maybe it reads some disinformation from Reddit, or maybe it reads some English document from before modern English. These are all things that can make your model worse. And it turns out that having some way to automatically evaluate how your model gets better over time really is useful. Now, I want to be really clear about this as well, because it's an important point. Evaluations are not everything. The way that I like to think about this is if you have a child, someone who has perhaps not much intelligence, standardized testing actually will tell you the difference between what is a smart child and what is perhaps not a smart child. Because actually, the sum of things that they could know is probably relatively small. By contrast, by the time you get someone who is very highly educated, the model that is good for you, or the person that is good for you in your business, might not necessarily be separable from someone who isn't good for your business based on standardized testing, right? It's more of how friendly they are, how much you like to talk to them, how helpful they are. These are all very soft things. They're very intuitive, I think, to people. And so even though we have this evaluations thing here, I want to stress that at Poolside, we do a huge amount of manual vibe checking. So it's a company-wide effort. If there are salespeople who want to try a new model, they're more than welcome to at any stage of training. And our engineers do the same thing. We really interrogate our models as often as we possibly can to make sure that they are going in the right direction. One real crucial advantage of this is that often your models are really bad at one thing in a particular area. So for example, me personally, I can't speak French. If you ask me a question in French, it would be clear that I don't know it. Now that might be a flaw of me as a person, maybe not, but models fail in a similar way, right? Often they have gaps in their knowledge that are very systemic. And it can be useful to interrogate them personally to see, okay, what is the gap in their knowledge? How can I improve this overall thing? Now, one of the things about evaluations is that you need a way to actually run your model. So we've just added another box to our diagram, which is an inference service. Now, inference is a very interesting area. We could talk about it for a very long time. But something I want to point out is that it is not necessarily clear straight away how you would co-locate training and inference in the same world, right? And this actually is primarily a scalability argument. You could use the same nodes, the same physical nodes, for training and inference. But actually, in practice, that means you can't scale them independently, right? You would have to scale up your training world to also scale up your inference world. And because we want to run this inference, right, we want to interact with our models during training, we need a quick way of transferring the weights that we've produced between training and inference without blocking either of them, right? If we had to stop our training every time to offload weights and then deploy them on evaluations, that's going to cost us a huge amount of time. And the whole purpose of this is to enable us to build better models faster. And so one of the lines on this graph that's actually been very crucial for us is having a way to move weights between our pre-training and our inference. And this makes it very easy to look at how your model is evolving, how it's getting better, all of these things. We'll come on to this later, but I think it's an important point to mention here. One of the very good ways to choose between different model architectures, if all else is the same, is how capable they are at doing quick inference. So we have some models that on evals or when we're doing our preliminary ablations actually perform very similarly to each other. And a good way to choose between them is see, okay, which one has better inference in practice? And of course, we optimize, right? We take these models once we've picked one and we do lots of tweaks to make it as quick as it can be. But making sure there are no fundamental reasons why your model is slow actually is a really good thing to do before you invest in a huge training run. Now, once we have this, you can make decisions about trade-offs. So I've mentioned this already in the context of making sure that your model has quick inference, but actually there are lots of other places where this is useful. Normally when you're building a model, in your head you have a parameter budget in mind. Let's say, I don't know, you want to build an 80 billion parameter dense model or a 500 billion MOE model. These are parameters that you can spend in many different places, right? You could make your embeddings bigger. You could have more parameters allocated to your MLPs. These are all parameters that you can spend. And when you have these insights, suddenly you can be very informed about what the model actually should be like and balance it against all of your requirements as a business. Now, I want to give you an example of where this sort of thinking can really help you. So historically, as a company, Poolside has operated under the thesis that if you make models that are good at writing code, they're also generally capable. Now, this was a little bit of an out there thesis when we founded the company in 2023, but it's gradually become more mainstream, right? Companies have started releasing coding products for their models, and I think they're all seeing a similar uplift that we've seen. When you have a model that is good at writing code, it turns out those skills really transfer over to other tasks. Now, I want to be clear here, what I'm going to talk about in a second is not just limited to coding, but coding is a good place to start. So I think, personally, that the way that pre-training works for specific skill acquisition is nonsense. Think about it like this. If you wanted to learn to write C++, you would never read every single C++ program that had ever been written. It would be nonsense. You would never learn to write code because you never actually do it. You're just acquiring information. And it turns out that the same is really true for foundation model building. So one of the things that we do at Poolside is we enable our model during training and also at various points post-training to interact with a coding environment. So you can think of this like a Docker container or some virtual environment of some kind, and you give it tasks to solve. Now, these tasks can really vary in difficulty. They can go from add a doc string to this Python function to implement this entire epic in this repository. The whole point is that you should be able to stack these in a way that enables the model to learn better, right? You wouldn't give a kid a PhD-level math problem. You would give them a question about addition. The same is true of models when you're trying to get particular capabilities. Something else to note is that although this diagram has this going into the pre-training box, this whole thing can be slid along an axis, pretty much wherever you want. If you wanted to do this sort of learning during pre-training, you could. If you just wanted to do it in mid-training or post-training, you also could. Right? There's no reason why this has to belong into the pre-training box. It's just for the sake of this diagram. And very crucially, when we're talking about RL in particular, there's no reason why we need to limit ourselves just to code. Right? Anything where the model can learn signals from what it's doing, and there's a rich variety of signals, can be modeled like this. It doesn't just have to be programming, right? It could be translation. It could be anything where there is a clear structured signal from which the model can learn. Now, something that is not strictly within the realms of model building is that finding these problems inside a business can be very difficult. Inside an enterprise can be very difficult. We've recently launched a forward deployed research engineer, essentially function as part of our company, to help you find these problems. And if these problems exist and we can integrate them into our model pipeline like this, you will be able to benefit from an uplift in model capabilities at that task. So if there is a task that is suited to this sort of setup, if you imagine the code execution box doesn't exist, then that's something where the model can learn and grow at that particular task. Now, once we have this, the only thing that's on this side of the diagram that we haven't spoken about yet is actually adjusting the model itself, right? I mentioned earlier that you can choose when to spend your parameters, but we haven't really spoken about it so far. Normally, what happens here is you have some idea that you want to try. Let's say you want to have more embedding parameters or more experts active in your MOE or any of these things. And it's useful to be able to express these very succinctly. So in practice, this box here on the left-hand side, the model ablation platform, is essentially a collection of for loops inside our internal repository. You specify all of the parameters that you want, let's say the number of experts, and our system automatically takes those and launches a training run for each of them. Now, normally it's on a small model, so we wouldn't train a huge model on this, maybe a few billion parameters, but normally this is enough to give you a sense of whether you're in the right direction, if you're going along the right path. I liken this to having children at school, right? If the class is bad, chances are you'll be able to tell they aren't learning very quickly, and it's the same with this. And you wouldn't waste your time with that child in that class if it wasn't going well. So having this system here really helps you to take your model and understand whether it's going to be viable for you. I think you already have noticed from what's been on the slide so far that there's a huge amount of coordination that's needed for this. If you take away nothing else from this talk, it has to be this slide, which is that a great deal of modern AI model building is essentially systems work. It's about making sure that your training proceeds reliably. It's about making sure that your chips are performant. It's making sure that you don't have any networking bugs. It's about making sure that all of these systems can talk to each other in a way that doesn't slow any of them down or doesn't harm the design of any of them. Now, I say systems here and not distributed systems because actually there's a lot of traditional systems programming as well, right? Making sure that your kernels are very quick, making sure that you can read files without going onto an out-of-memory error. There's lots of things here that are not just distributed systems. And something as someone who is more of an engineer than a researcher these days, I find that doing this work really enables people who are much smarter than me to do their best work at Poolside, right? To actually be able to research and understand their own ideas more quickly than they could anywhere else. It really enables them to not have to think about the minutiae of scheduling jobs or making sure that their nodes don't crash. The systems that we have built handle all of that for them. And so they don't have to worry about that. They don't have to spend their hours debugging trivial things They get to spend their hours thinking about big problems and coming up with solutions to those problems. Now, I've said that a great deal of modern model building is systems work, but I want to stress the rest is science. And when I say science, I mean a very traditional science. I mean empiricism. I mean you have a hypothesis, you test that hypothesis, you see how it went, and you repeat this process over and over again until you end up with something that is good. I think this is not really understood by the outside world because the thing that they see is the outer product, right? It's the big model release that everyone makes a lot of noise about. It's the DeepSeek moment. It's all of these things that are very, for want of a better term, hype, but it doesn't really reflect the hard work that goes into building these models in practice. One of the things that any of you who have done science in any serious way will know is that your data is everything. Keeping track of your data and being able to understand what it is that you have done to get to where that data is now is incredibly important. I mean, even those of you who plotted graphs at school will know that you had to be aware of outliers, and AI is no different. So one of the key pieces of this model factory that we're discussing today is having the ability to transform our data at scale. Now, this can be as simple as getting rid of non-permissive licenses from your training data set, making sure you aren't training on anything illegal, but it can also be as large as doing deduplication, right? Making sure that the model doesn't see too much of one particular data, and so it doesn't overfit. Being able to track all of that and being able to make sure that you have a very consistent lineage, like a chain of custody for everything that you've done along the way, is a really important way of making sure that you understand, okay, I fed this into my model, and this is what happened. This is why the loss went down, or this is why the loss went up. And there's lots of really clever tricks that you can play to incorporate this whole system together. So for example, one thing that you can do is during your training, if you build such a thing, you can uniquely link loss spikes back to the data sample that caused those loss spikes. And that information enables you later to look at your data and go, actually, you know what, that sample was out with distribution, or actually we really want this in our training data set. Let's try and get more of it. There's lots of clever tricks you can play when you have this sort of systems view of your training. Now, one of the things that the AI industry doesn't tell you very often is that we all train on various rephrased forms of web data. Now, everyone tells you that they train on the web. That's no secret. But training on web data as it is just purely scraped often is not what is best for your model. What is good for your model is to have data that is expressed in a particular form. Right? I don't think anyone here in this room has learned anything difficult by reading raw text snippets from the internet. Chances are you learned from a lecturer or from a book that you studied yourself that had already been organized in a way that made it easy for you to learn things. And one of the great things is that you can do this very similarly with synthetic data generation. Now, to be clear, this requires you to have access to inference again, right? Because you need to query some model that does the work for you. But you can already see how this diagram really stacks on top of itself, how all of these boxes are beginning to interact with each other in a way that enables them to be more than the sum of their parts. Right? Inference by itself is very useful, but when you can use it to generate more data, suddenly that means you can make better models, which also means that they can be more useful for synthetic data generation. So the whole thing really builds on itself when you have a diagram like this. Another thing that you can see is highlighted on this slide is this blender box. Now, historically, when you've trained a model, what you have done is you have chosen the number of nodes you want ahead of time, you've distributed the data set to those nodes, and then they have run off and done the training. This is fine, and it kind of works, but actually there's a lot of limitations to it. So one of the limitations to it is that you have to have your data ready ahead of time, right? You can't stream data to these nodes, as the way I've described, because you have to pre-distribute your data set. Equally, it makes it really hard to scale up your training in any meaningful way. It's quite easy to scale down because you just take some pool of nodes and you shrink them. But if you want to scale up, you've got to redistribute your data set. That also can be a real pain if you've got to replace a faulty node, right? Let's say you've got 8,000 GPUs that are being used and one of them dies. Well, suddenly you have to add a new machine in and you have to preload the data set onto that node. And that's really tough, right? It makes your training much more difficult than it needs to be. So one of the things that we do at Poolside is we stream data directly into our training nodes via this service that we have called Blender. Now, as the name suggests, Blender also produces data blends. So you'll mix multiple different data sources, Shakespeare, code, all of these things. Because it turns out that, much like a kid at school, you don't want to expose your model to just one thing at once, right? If you only read Shakespeare and then suddenly you learned C programming, that would probably be quite confusing. And the same thing is true of models, right? They like to be taught multiple things at once, admittedly in a structured way, so that they can keep things in their head whilst they're learning. One of the other great things about streaming data into your training is that filtering and producing data is incredibly time-consuming and expensive. I probably estimate that on any given day, admittedly when we're not doing anything else, the vast majority of our GPUs are used for synthetic data generation at any given time. If you had to wait for those to be done, that streaming process that preloading into training would set you back by weeks. You can't afford this if you want to be at the frontier. You've got to be able to continuously improve. And so one of the great things that Blender allows you to do is to stream your data into your training nodes. It turns out that this has other advantages as well, because you can adjust things on the fly, right? If you suddenly decide that you need a new blend or a new data mixture, or you want to add another data source, streaming enables you to do that very easily. And so all of a sudden, you have many advanced techniques that you can play with when you come to train your model, right? Maybe you see your loss curve going up halfway through and you think, I need to add more Fortran code to this. Okay, that's very easy to do. If you pre-distribute everything, that's way, way harder. And even things as simple as like tokenizing your data or packing your documents into one big form is not necessarily theoretically very difficult, but the practicalities of it kind of get quite thorny quite quickly. And having a service like this that handles it all for you really enables you to move quickly and have new ideas that you can actually act on. Now, I mentioned earlier that we do a great deal of vibe checking at Poolside, and so it's only right that we have this box right at the end of pre-training and also post-training. This, it turns out, is actually very useful even on partially trained models. So I mentioned earlier, maybe your model has got some common failure case, right? Maybe you can interrogate this early. But actually, one of the things that we have found this enables is for members of the Poolside GTM team that are in customers to give us feedback about what doesn't work. Oftentimes, it's really difficult to get in-field information because there's a huge number of people that are between any given person. But when you have an introspection platform like this, it becomes really easy to drop bad samples into this and for people to go, oh, hey, this thing doesn't work very well. And it really enables everyone at Poolside to be part of actually building the models. It's not just the domain of the researchers that actually do the nitty-gritty hands-on work. Everyone, from our head of HR to our communications director to everyone in between, plays with our models and uses them to get a good understanding of what's actually going wrong. And even, some people in the company very recently have picked up vibe coding as well, which has been quite fun when they haven't had any coding background before. And that is a really good testament to how effective this is. Giving everyone the ability to actually play and interact with the model suddenly makes it much more of a community thing rather than just some people who work on pre-training thing. Now, I'm sure you've all noticed by this point that this box originally only pointed to the pre-training step. But it should be clear, right, that actually you want to be able to ablate everything. There's nothing here that shouldn't be subject to some fixing. So to be frank about what I mean, normally what we do is we fix some particular piece of the architecture. So let's say the model architecture or the fine-tuning that we're going to use or whatever. And then we alter any of these pieces independently to see what happens. This in general is just good science hygiene, right? You try not to move too many variables at once because you can have confounding effects. But in terms of model building, it actually really matters. And again, this is really a limitation of 2D space. Every diagram or every box on this diagram should really talk to every other box, right? Our model ablations actually also happen in code execution. We don't use every code execution task for every model. We don't use every reinforcement learning algorithm that we've got for every model. We don't even run the same evaluations necessarily on every model because they might not be relevant. And so having the ability to adjust any piece of this really easily and quite frankly seamlessly really enables you as a company to move much faster than you otherwise would be able to. This diagram is also horribly incomplete and out of date. I apologize for fitting on such a small slide. There are probably somewhere between 50 and 100 such boxes like this in our model factory at any given time. And probably every week we end up with a new one. This system really ever evolves. When we first built it, it was much like the system that I described to you earlier on, right? We had these 3 boxes, then we added evaluation, then we added inference. But actually it continues to evolve as our needs as a business change, our needs as a frontier company change. For example, one of the boxes that was not on this previous slide was quantization. So the ability to take your model and shrink down the size of the weights or the activations or any of these things. It turns out that that is also something that you really want to be able to play around with, because maybe a quantized model in one place might be substantially worse than the original model. But maybe certain architectures, when you tweak them, are more, let's say, resilient to quantization. Knowing that is really important because it means that you can make informed decisions about the models that you're actually building and training. And so having some capacity or some ability to accurately look at these things really matters, and having the ability to adapt this system really matters. Another thing that's really important about the model factory is that it serves as a basis of everything that we do in the company. Whenever a new joiner joins the company, normally there's some time that it takes them to get up to speed. And invariably there's some moment of, have you tried this? Have you thought about that? Having a system like this enables you to point new people to the things that you've already done, or the data sources that you're already using, or the RL algorithms that you've implemented. All of these things together are important to get people to be efficient. And I mean, even me, I've been at the company nearly since founding, and there are things that I think about every day that people have thought about months ago, and I've just not asked them yet. And being able to go and check and go, oh, okay, they had this idea, great, it worked, or great, it didn't, is really very useful. It decouples the work from the workers. It means that people can have insights independently. And actually, it's one of the real strengths of this sort of way of engineering is that other than like scheduling constraints or just team and company missions, you're able to be much more effective individually than you would be if you were doing everything in the old-fashioned way, right? I can sit on my computer, I can launch a training run, assuming I've got enough compute, and then I can have an answer very quickly. And providing there's enough compute in my compute queue and I don't have to do something that's more pressing, we can have these insights. And it enables us all to move much faster. It enables us to be much closer to the frontier and crucially to continue being at the frontier as time goes on. It also acts as a real ultimate source of truth. I think AI as an industry is one that is very full of opinions. I think if you asked anyone here about their opinions on transformers versus linear attention, AMD versus NVIDIA, which company is going to win, all of these things are ultimately opinions. And it turns out that having an ultimate source of truth of, no, we tried that, it didn't work, or no, we tried that, it looks promising, or even just having the ability to experiment over a conceptual disagreement, really helps you to understand what it is that you're doing, and it removes a lot of the noise, right? I personally don't ever look at Twitter. I don't ever see what anyone is posting about the models that they're building, because I know that if I'm interested and I find an idea, I can try it. And if it works, great, perfect. This enables you to really decouple yourself from everything else that is going on in the outside world, and it enables you to focus on your mission and what's happening. You don't have to think about what anyone else thinks is the latest and greatest idea. You yourself can try it. And having a system like this really, I must stress, does enable you to experiment with things very easily. If there is a new attention variant or some new post-training algorithm or QK norms versus layer norms versus RMS norms or any of these things, you can adjust just that piece and leave everything else the same. And it means that you really don't have to deal with all of the amount of minutiae that you would otherwise have to handle when it comes to evaluating these ideas and seeing how they actually work. Something to point out, I know I've already mentioned this briefly, is that the factory really grows from itself. So one of the good examples is that in our code execution environment I mentioned before, for a long time we had very static rules, right? This is a C project, okay, run make or run GCC. This is a Python project, okay, run pip install. But actually, that's very far from how a human does this, right? What a human does is they look at the README, they look at the installation instructions, they follow the steps. If it's a C++ project, it's probably missing some dependencies, and so you install those. And then you get something that works. It turns out that agents are also really good at this. And so what we did was we built an agent that would build these environments for us, that would build these containers for us. And when you have that, that enables you to build better models, which in turn means you can build better agents. And you just can see how this process really builds on itself to keep you moving very quickly and enabling you to do things that you couldn't do otherwise. It means that you can really benefit from your own good work almost immediately. Synthetic data generation, as I mentioned earlier, is another example, right? As your models get better, they're much more capable at rephrasing, annotating, synthesizing, which enables you to train better models later on. This whole thing really builds on itself and enables you to compound. I think as engineers, we all know that good abstractions compound, right? This is one of those classic things that you're taught as an undergrad, but it's also very true in AI. When you get that architecture right, or when you have built something that you know you can stack on top of itself, suddenly you see benefits immediately, both from a model perspective and from a systems perspective. Now, I've spoken a lot about the theory so far, but I want to give you a sense of what this actually looks like practically and what this looks like on a day-to-day basis for someone like me who works on it. So one of the key aspects of all of this is what we term an asset. Now, an asset is essentially a versioned piece of code and data in some directed acyclic graph. And the crucial aspect of any asset that we have is that you can regenerate it from scratch on demand. Every asset is linked to the exact git commit of the code that was used to produce it, the exact data sets and the lineage that were used to produce it. And what that enables you to do is, let's say later on you think to yourself, you know, I had a bug in my data processing pipeline, or I really just want to see, you know, if I do this again, will I get the same result? Suddenly you have the ultimate ability to reproduce things. And I want to be clear, even though you might have the same code and same data, you might get a different response or a different result. And this is because obviously you're dealing with systems, right? Chaotic systems. Maybe your node died, but died silently, and so that affected the computation of some activation or something like that. Having the ability to reproduce things on demand really matters. And crucially, when you have everything structured in this way, running new experiments based on old stuff is really easy. Because what you can do is you can take the asset configuration that you had before, you can fork it, much like you would fork something on Git, make an adjustment, and then run it. And all of the previous lineage, everything you've done, all of the code that you had before, stacks on top of itself. And suddenly you're able to experiment in new and very exciting ways that you just couldn't do before. This is an example of what I mean. So you can see these, our actual graph is much, much larger than this, and this is just an artist's rendition. But you can see what happens here, right? We have all of these different boxes that feed into each other. Now, that vertical stack that's second from the right, you can see is a deduplication stack. And you can see that each of them end with a different number. This, it turns out, is the percentage similarity parameter that we used when we were doing deduplication. And you can see here how all of these boxes feed into these other boxes and enable you to experiment more than you otherwise could, right? If I wanted to add a code 0 dedupe 40 box, I could also do that, right? There's no reason why this needs to be the way that it is. I can play to my heart's content with these different parameters. And then when you have these, you can feed them into the next thing and the next thing and the next thing, right? Deduplication doesn't have to be the last thing in your pipeline. It can be the first or the last or somewhere in the middle. Maybe you run it twice. Who knows? There's lots of things that you can do when you have a system that is structured and built like this. Another thing that you really need is the ability to schedule jobs on your cluster. So at the moment, we have something like 10,000 H200s that we use. We have more coming soon. But having all of that compute only means something if you can effectively utilize it. And it would be really silly to just say, right, we're going to use all of these GPUs for training all of the time. Because actually, sometimes you're just doing something else, right? You don't want to do a big pre-training run. You want to do data generation, or you want to do fine-tuning, or you want to do reinforcement learning. And sometimes you don't even need a whole node for the job that you're doing, right? If you have a really small model, you probably don't need a whole 8 H200s to run that. You could probably run it on just one. Having the ability to schedule jobs on machines in arbitrary ways and ways that actually grow and shrink depending on the work that you're doing is really key to having a system like this. If you don't have something like this, you're always going to have wasted compute. You're always going to move more slowly than you otherwise could. And ultimately, you're never going to get to the frontier of things because someone else will have that advantage. So having the ability to schedule jobs essentially arbitrarily and crucially not having to worry about that as a researcher really is one of those things that enables you to move quickly. One of the other good things about having a really robust scheduler is that you don't need to worry about failed nodes because every job is a configuration, right? I mentioned before that everything was an asset. So if I detect that a node has failed during some pre-flight check or during the actual job itself, I can just switch that node out with another one, and everything is good, right? I don't need to worry about having to do systems configuration myself or setting up the networking or anything. It all just works. It also, as a system, has a distributed logbook associated with it. So I mentioned before that we have this directed acyclic graph, but actually each of those also link out to various metric platforms as well. And we collect all number of metrics, right? We have our traditional training metrics, but we also record a huge amount about the efficiency of various jobs, a number of GPUs that they use, when they were busy, when they were idle, their power draw. Collecting all of those things really enables you to do a lot of things. So for one, it enables you to look at certain workloads and go, do we need to make this faster? Or actually, can we scale it down, right? Maybe it's mostly waiting for network most of the time. Well, perhaps we don't need as many GPUs then. It also crucially enables you to get more insights about reliability. One of the things that we've seen is that nodes tend to fail under certain workloads. So if you're running many matrix multiplications back to back to back, chances are that's going to overheat your GPU. If we detect that that workload is there and that workload is actually crashing nodes in practice, there are more precautions that we can take to make sure that that doesn't happen. And again, sometimes you're just unlucky, sometimes things happen, but having a log of every single thing that you did and every single thing that has happened and will happen is a really good way to make sure that you're not missing out on insights that would enable you to get closer to the frontier. I want to talk briefly about how all of this feeds into large-scale training runs. I think large-scale training runs are kind of the big headline number that everyone gets excited about. Right? When you saw last year that DeepSeek released a model that was trained on only a few thousand H200s, or when Mr. Owl yesterday announced that they trained their large model on only 2,000 H200s, everyone always talks about the large-scale training runs. And it makes sense, right? It's the thing that gives you the most eyeballs. It's the thing that talks about the most money. It's clear to see why we like this. But what I want to point out to you is that there's actually not that much difference between the large-scale training runs and the small ones when you have a system like this. So this diagram that I showed you before of the asset flow is exactly the same no matter whether the model that you're training is big or small. All you do is you tack another box on the end, you specify more GPUs or a different configuration in some way, and that's it. There's no distinction in our system between small models, a 7 billion parameter model, or a 5 trillion parameter model. You just adjust what it is that you have in your configuration in some way, perhaps some way that's determined by research, and that's it. And everything I've said to you so far is also true for those big runs, right? You can interrogate what's happening with your workflow. You can see where the network is slow. You can see, oh, hey, actually, maybe we need more GPUs, or maybe we can get away with fewer. All of the insights that I've mentioned so far also hold for big models as well as small models. So you don't have to worry about whether your big model is training well or whether your loss spikes, because you'll know if it happens. You can sleep soundly. And on a personal note, one of the things I love about this system is we all sleep soundly, because actually it's really reliable. In times gone by, engineers would stay up all night to make sure that their training didn't crash. Or if it did crash, it would be all hands on deck. Now we mostly have automated systems that recover these things for us. Sometimes, granted, there is a need for manual intervention, but that is way less common than it is almost anywhere else. and it's way less common than it used to be even for us. Most other companies have whole teams that are just dedicated for babysitting a training run. We do not. And that is a crucial thing about moving quickly. Because let's face it, your headcount is an expense. Hiring more engineers in AI is a very expensive thing. And if you can scale and compete with people without having to hire ever more people, there's a lot more you can do, right? You can have more GPUs, or you can afford to get better people. Or alternatively, you can enable the brilliant people that you've hired just to do the work that they actually care about. I don't think anyone goes into AI because they want to wait all night to fix some scheduling issue, right? They want to build AGI. They want to solve hard problems. Having a system like this enables that. It enables you to get people who want to move quickly and to enable them to move quickly. They don't have to deal with internal politics. They don't have to deal with systems that are flaky and don't work. You have this whole system and it just works for them. And it enables us to move so much faster. It enables us to punch well above our weight, and it enables us to stay ever closer to the frontier. Ooh. Before I wrap up, I just want to point out that actually, comparatively few GPU hours are actually spent on the big training run. It's a real misconception in the industry. Everything I've spoken about so far has been based around, doing ablations on small models, or playing with different parameter mixtures, or playing with new RL algorithms, or things like that. This is very much the case, right? We spend our GPUs on those things, on making sure that our model can scale when it does scale, making sure that the new algorithms that we've trialed play out on a small scale, making sure that our data mixture isn't just horrendously awful, right? We stack all of these things together at a small scale. And I promise you, every other foundation lab in the world that makes models does the same thing. The reason why DeepSeek were able to produce such a good model nearly a year ago was because they had tried many small optimizations and tweaks and ideas, and then combined them together to make a model that was good. And all of those ideas probably had to be tried independently, right? I don't know, I wasn't there. But I can't imagine that you would make all of those tweaks just on a whim, right? Chances are you're at least going to look at it first and go, oh, actually, that means something, that's important. And it turns out the same is true for us, right? We spend comparatively few of our GPU hours on a huge training run. It's more the ta-da at the end of the year, or during some point, right? We go, oh, actually, we're ready. Let's train a big model. And then it proceeds for some weeks, but actually, ultimately, that's not where we spend most of our time. That's not where we spend our thinking time. One of the things about having such a system, though, is it gives you the confidence that if tomorrow you needed to train a new big model, you could. Right? If someone came down to me and said, Joe, we need to train a new state-of-the-art model tomorrow, can you do it? This system gives me the confidence to say yes. I don't have to worry about how we're going to get there because the system enables you to already have those insights in place. We have many buns in the oven, as it were. Right? We're constantly iterating over these things, and at any given point, we know what we need to do to improve our model. Having a system like this really enables you to have such confidence in what it is that you're doing. And actually, as someone who works there, that really matters, right? Knowing that we can keep up with everyone else, despite having a much smaller team, is perfect. That's what I want. I want to have that confidence. And having a system like this gives that to you in spades. With that being said, if you're interested in going from being artisanal to being industrial, we are hiring. All of our open roles are on our website. And if you're interested in what I've spoken about, we're at booth 802. So please feel free to head down and come and say hello. And with that, I'd like to thank you all for listening. If you've got any questions, I'd be happy to answer them.